Good morning. Um, Welcome today to Tuesday. Um, Today we're going to talk about properties of relations. But before I start, are there any questions about any of the material we've covered so far in chapter 4 or anything else for that matter? Okay, well, with no questions, I guess we'll launch in. So the first thing that we're going to do is a problem involving relations. So we talked about composing relations before, and here's an example that I want to go through with you in class today. Let's switch to a nice red pen and then look at it and say, well, I have two sets, two diagrams. I have R that goes from this first set to the second, and S that goes from the second to the third. And we want to know what the composition is of S of R. Okay. So does anyone want to start out and give me some clues where we are here? Okay, I guess I'll do it. Today it's a quiet day here. So let's start out and we trace it from A goes to 1 and 1 goes to 3 different places. So we have to then have A going to 3 different places. A goes to 1 and 1 goes to 1, 2. So now we have A going to 1, 2. A goes to 1 and 1 goes to 1, 3. So now A goes to 1, 3. And A goes to 1 and 1 goes to 1, 4. So now A goes to 1, 4. Those are the first 3. But now we have A goes to 4 also. So now we have to look and see, where does 4 go? Well, 4 goes to 3 different places as well. So now we have A goes to 4 and 4 goes to 1, 4. Well, that's okay. We already have 1, 4. It got there a different route. And then A goes to 4 and 4 goes to 2, 4. That's a new one. So now we have A goes to 2, 4. And then we have A goes to 4 and 4 goes to 1, 4, 2, 4, 3, 4. So now we have A goes to 3, 4. So A goes to almost everything else in the little set diagram. That's the final set that we're going to. So now we move on. This is going to be a very messy diagram. So now we have B goes to 2 and B only goes to 2, but now 2 goes to 1, 2. It's 1, 2. B goes, I'm sorry, 2 goes to 2, 3. So we go from here to 2, 3. And 2 goes to 2, 4. So B goes to 2, 4. So we have B going to 3 different places. Okay, now notice A went to 3 places in the relation R, and it goes to 3 places. It goes to 6 places in the relation S of R. B goes to 1 place in R, but it goes to 3 places in S of R. So now we go to C. C goes to 3, and 3 also goes to 3 places. So 3 is going to go to, C is going to go to 1, 3. 1, 3. C is going to go to 2, 3. C goes to 2, 3. And C is going to go to
3, 4.
Oh, thank you. 3, 4. So I'm not going to finish this because it's getting very messy because it's so big. But I think you get the clue about how to deal with this. Are there any questions? Dane?
Yeah, I'm wondering if can you compose two relations to make a function, even if the first relation is not itself a function?
That's a good question. Maybe. Well, yes, certainly. So if the first one isn't a function, but the second one, say, maps to all the same point. So if the second one is not just a function, but some very special kinds of functions, you can do it. You may be able to do it with a different kind of relation as well. But generically speaking, it's not generally true, but it could be if you carefully designed it.
Cool. Thank you.
Okay, good. So here we have another one, and this one's a little more complicated. In this problem, we're looking at function composition, and we have the function f and we have the composition, and we're saying, what is the function g? Okay, so we know the end result and we know the first mapping. So we're asking the question, what is the second mapping? Okay, let's see if we can follow it along here. So in this mapping, a goes to 1. Remember, this is a function now. So a goes to 1, but in the final, a goes to, I think that's an epsilon. A goes to epsilon. So where would 1 go to in this middle one?
Epsilon.
Yes, 1 has to go to epsilon. You all see why? Okay, let's try this again. B goes to 2, and here B goes to delta. So where does 2 go to in the middle one?
Delta.
Yep, good job. Okay, now C goes to 4, and here C goes to alpha. So where does C go to in function G? I'm sorry, where does 4 go to in function G?
4 go to alpha.
Goes to alpha. Okay, now we have X goes to 6. And in the final result, X goes to epsilon. So where does 6 go to?
6
Epsilon.
go to alpha.
Good. 6 goes to epsilon. And Y goes to 3. And in the final result, Y goes to, what do we have? C, let's say. Where does that go? Actually, that's a zeta, but we'll deal with that. Where does it go?
So 6 goes to C.
Y goes to 3, and 3 goes to
Y goes to 3. So 3 goes to
zeta.
C. Zeta.
Okay. Finally, Z goes to 5. Here, Z goes to beta. So where does 5 have to go?
5 goes beta.
5 goes to beta. Okay. So we filled it in. Does everybody understand how to deal with this composition? Now, if you're composing functions, filling it in can be a little more complex because we notice that you can end up at the same point from 2 different start points, going through several different values in the middle set in a relation. But in a function, every domain point has exactly 1 point in the codomain. So it's a little easier. Are there any questions? Okay. Let's jump into some new material now. We call a binary relation several different things depending upon properties. So a binary relation we're saying is on A. And that means that it's a subset of A cross A. And remember that we write A squared is equal to A cross A. Now that doesn't mean we're squaring all the elements of A. It means it's a cross product, and that's just shorthand notation. So we call it reflexive if every element is related to itself. Okay, every element, not some elements, but every element. Okay, for all A, every element. It's irreflexive phase. Do you have a question?
Yeah, I have some question just for the here have all the, it means all the element inside the relationship must belong the set A, or all the element in the set A have to appear in the relationship.
Yes, they all have to appear because A is going to be related to itself. So every element has at least one other element it's related to, which is itself. Very good observation.
Okay, so all the element in the set A have to inside the relationship. Okay, gotcha.
Yes,
So in other words, the set or the relation R has to have at least the same number of elements as the set A.
yes, if it's reflexive.
Okay.
Very good observations, both of you. It's irreflexive if A is never related to itself. Never, never. Now, you can have relations that are neither. You can have relations that some elements are related to themselves and others are not. Okay, in that case, they're neither reflexive nor irreflexive. Okay. All right. So we have three possibilities related to reflexive. We have reflexive, irreflexive, and neither. Okay. Now, a relation is called symmetric if for all, notice this here, for all AB in the set A, that A related to B implies B is related to A. Now, what that means is that every two elements need not be related to each other. But if they are, then the reverse is also in there. Okay? Do you understand that? So whenever there's a pair that are related, then if we flip who comes first, that's also related. Okay? Antisymmetric says for all AB, if A is not equal to B, we have to have A not equal to B here, and AB is in the relation, then BA is not in the relation. Okay? So once again, if I have two arbitrary elements, they may not be related at all. But if they are related, A is related to B, then if it is antisymmetric, B is never related to A. Okay, so once again, we have three cases. It can be symmetric, antisymmetric, and neither. Okay. Finally, a relation is transitive if and only if for all A, B, C in A, if AB is related and BC is related, then AC is related. Okay? Now, you can have some that are related and some that are not. So in this case, there's nothing called anti-transitive, but there's something called transitive and not transitive. So not transitive could be if A is related to B and B is related to C for any one or more elements in the relation, but A is not related to C, then the relation is not transitive. Okay? It just has to fail for one set of elements, well, one pair of elements in the relation. Okay. A relation is called a partial order if it's reflexive, antisymmetric, and transitive. So let's think of a good partial order. Okay. And I'll tell you, the partial order is let A be R2. That's the plane. Okay. So we're taking any. So now we're going to say, give me a point X, Y, X1, Y1, and X2, Y2 in A. Now here, this is a little confusing, okay? Because in this case, what we have is there's a point that is our element. So these are not in the relation yet. The relation is going to be in R2 cross R2. We say X1, Y1 is related to X2, Y2 if the magnitude of X1, Y1 is less than or equal to the magnitude of X2, Y2. So do we remember what the magnitude is? Everybody remember what that is? Magnitude of a point in the plane is the distance from the origin to the point in the plane. So that would be, the distance is the square root of x1 squared plus y1 squared. We sum those and then we take their square root. Okay, so here we're saying that 2 points are related if one has smaller than or equal to magnitude than the other. So what that means, if I look at my plane here, here's 1 point, that's x1, y1. And here's another, that's x2, y2. Okay, and we're saying that if this line is shorter than that line, then x1, y1 is related, less than or equal to x2, y2. Okay, so let's ask the question, is it reflexive? Well, is the distance of every point to the origin equal? That's where we're getting the equal sign here, equal to the distance of itself. Yes, of course, they're the same. So it's reflexive. Is it symmetric, anti-symmetric, or neither? Okay. For 2 points that are related, if the distance from along the line from the origin to x1, y1 is less than or equal to the distance x2, y2, is it flipped the other way? Well, it would seem, the way I drew it, that no, it can't be. It's anti-symmetric, you would think. Aha, wait a minute. Let's pick an x3, y3 right here. And suppose x3, y3 and x1, y1 are on a circle. Then they're the same distance from the origin. In that case, x1, y1 is related to x3, y3, and x3, y3 is related to x1, y1 because they have the same distance. That equal sign makes a difference there. Okay, so that's a case where it's neither symmetric nor anti-symmetric because we found cases that are related in both directions, but we have other cases that are not related in both directions. If there's one element that fails the condition, it absolutely disqualifies it. Absolutely. Okay. Now, what about transitive? Is it transitive? Well, the answer is yeah, kind of. So we have if the distance from x1, y1 to x2, y2 is related, and x2, y2 to x4, y4 is related, then you can see that this distance is shorter than this, shorter than or equal to that distance. So it is transitive. So what we have is a relation that is reflexive, neither symmetric nor anti-symmetric, and transitive. Okay? Now, we can ask the question, what if instead of saying R2, we said that these were points on the real line? Here's the origin. Here's x1, y1. Here's x2, y2. Can the case that we had in the plane exist in this case? And the answer is no. We can't do that. If the distance, oops, sorry. Let's say it's R plus, so it's only the positive origin, positive side. So if we have that x1, y1, the magnitude, the length of this line is less than or equal to the length of that line, then they can't be reversed. X2, y2 is not less than or equal to x1, y1, the distance. So in that case, if we're on the real line, it is anti-symmetric. Okay, because the only time they can be related is if x2, y2 is x1, y1. Remember, the key for anti-symmetric says A unequal to B. So the 2 points would have to be different points. I don't know why I'm saying x1, y1. It's only x that we're looking at here, values of x. Okay. All right. And transitivity still holds because the lengths of the line, if I have a third point, here's x3, that's all we need. And here's the length of that line. So if I have the length of the line to x1 is shorter than the length of the line to x2, and the length of the line to x2 is shorter than the length of the line to x3, then clearly the length of the line to x1 is shorter than the length of the line to x3. Okay, so this last case is a partial order on, let's say, the real line, the positive real line. Okay, let's talk about other relations, okay? So up here in blue, we have the definitions of the different relations. And let P be the set of people who have ever lived, everybody from the first time of man. And let A and B be two people who have lived. Then we have a relation R, and we're going to call the relation R, A is related to B if A is a child of B. So what properties does R have? Is it reflexive? Can A be a child of himself or herself?
No.
No. So not reflexive. Is it irreflexive? Is it always the case that A is never his own child?
Yes.
Yeah, pretty
Yes.
much. Let's see, what about symmetric? If A is a child of B, is B a child of A?
No.
No, no. Notice not symmetric is different than anti-symmetric. Okay. What about anti-symmetric? If A is a child of B, is it always the case that B is not a child of A?
Yes.
Yes. So it is yes to anti-symmetric.
Are we saying that a grandchild is related to their grandparent?
No, we haven't gotten to transitive yet. We said a child, not a descendant. You picked up my next question, so hold on to that a minute. So finally, is a transitive. If A is a child of B and B is a child of C, is A a child of C?
No. Based on what you just said.
No, unless you have some really weird families. So we'll say no. So no, not transitive. Now notice that even if we have some weird families, the rest of the families don't have that property. So that makes it not transitive. Okay, now someone already asked my next question. What if we replace child with descendant? Does anything change? Okay, well, let's ask.
It
what
should be
changes.
transitive now.
Yes, very good. Then yes to transitive. Very good, thank you. Notice we have different colors for that. Okay. Let's go on. Oops. Well, okay, we got practice problem 4, but they're mislabeled from here on out. So let R be a relation on Z given by the rule that A is related to B if A minus B is even. Okay. Prove that R is symmetric, but let's ask more questions. Let's say, is R reflexive? That's our first question. Is R reflexive?
Yes.
For A in Z, is A minus A, which is equal to 0, which is equal to 2 times 0, even? Well, yeah, that's the definition of even. So A is in R. If, let's see, if A, B is in the relation, then A minus B is equal to 2K for some K in Z by the definition of even. Right? That's the definition of the relation. Okay, then multiply both sides by -1. And that leads to B minus A is equal to minus 2K, which is equal to 2 times minus K, which is equal to 2 times P equal to minus K in Z. So BA is in the relation. So it is symmetric. Well, let's ask the final question. Okay. transitive. We'll prove a little more than we were asked. If A, B is in R and B, C is in R, then A minus B is equal to 2P and B minus C is equal to 2Q. P and Q in Z. And that's by definition of even. Okay, so how are we going to prove the final thing? We're going to say, well, A minus B plus B minus C. What's that equal to? Well, if I do standard arithmetic, that's A plus minus B plus B minus C. That's it by associative, which is equal to A plus 0 minus C, which is equal to A minus C. This next one is inverse. The second one, getting rid of it, is identity. And that's equal to A minus C. But no, wait a minute. What was A minus B? That was 2P. And B minus C is 2Q. So that's equal to P minus Q. That's distributive law. And that's equal to 2C. C equal to P minus Q in Z. That's by closure. So we have now had a relation that is reflexive. It is symmetric, and it is associative. Okay, so we've got all three properties so far.
You mean transitive?
I'm sorry?
I say you said associative, you mean the transitive?
Yes, thank you. Wow, my head's there. It's, yes, transitive. So relations aren't necessarily associative unless you put three together. Okay,
Dr. Cohen,
yes.
could something be both symmetric and anti-symmetric? If it's,
No,
what if the relation has a single pair and that pair is just the same thing, like it's 1 and 1? Because that would seem to me, the symmetric definition does not require that they not be equal. So it meets that requirement. And it meets the anti-symmetric requirement because the hypothesis of the conditional is false. So that makes the whole implication true, doesn't
you're
it?
right. Okay, I revised my statement.
Okay, thanks.
Okay, now, yeah. Okay. So let's look at a graph. This is the one arrow diagram, and ask the question, what properties does the relation represented by this graph have?
Reflexive.
I can't hear you, I'm sorry.
Reflexive.
Yes, it is. Why is it reflexive?
Each node has a loop.
Each node has a loop, yes. So that makes it reflexive. Everything is related to itself. That's a requirement for reflexive. Does it have any other property?
Anti-symmetric.
Transitive.
I'm sorry?
It's anti-symmetric.
Anti-symmetric. Let's see. Are there any arrows if there's an arrow from A to B, are there any arrows back from B to A? I don't think so. I don't see any. So yes, it is anti-symmetric. What else?
It's also transitive.
It's also transitive. Very good. Why is that the case? Well, here I have an arrow that goes from this node to this node, and an arrow that goes from that node to that node, and an arrow that goes across like that. And then I have another arrow. If I have an arrow from this node to this node and one from here, then I have one that goes from the beginning to the end. Okay, what else do I have? Well, I have an arrow that goes from the second point to the third, and the third to the eighth. And then I have one that goes from the second to the eighth. So whenever I have one incoming and an outgoing, then where the incoming originates and where the outgoing goes is also in the relation. So yes, it is transitive. Very good. I think we covered it.
In these transitive, or in these arrow diagrams, is it always true that transitive relations have triangles? Because it seems
Yes.
like every time we have, yeah, okay.
Good observation. Very good observation. Be careful though, because you've got to watch the order of the triangles. You've got to watch where the various points go. Okay. Okay, now we have different kinds of orders. So we talked about what a partial order is. It's reflexive, anti-symmetric, and transitive. A strict partial ordering is irreflexive, anti-symmetric, and transitive. So can anyone think of a strict partial ordering?
A set with just 1, 2 in it.
I'm sorry, say again.
Would a set with just a number with just the pair of 1, 2, like that relation?
What's the relation?
X equals 1, Y equals 2.
That is indeed irreflexive. Is that anti-symmetric? It's transitive by default because there's nothing else there. Again, okay, let's pick something that's not a morbid case here. And the one would be less than. Not less than or equal to, but strictly less than on the real line. Okay, not magnitude, just less than. So A is related to B if A is less than B. So that's irreflexive because we can't have A equal to A. It has to be less than the one on the right. Yes, Christopher.
I'm just wondering if the last example that David offered would be transitive, because if one goes to 2, doesn't 2 also need to go to 2 for it to be transitive?
No, what we have, remember what the transitive rule says is if A goes to B and if B goes to C, then A goes to C. Well, we have no examples of B going to C. So this is a case, remember, where we have the empty leading to the positive, the negative leading to the positive in some case. So the hypothesis is not fulfilled, so the conclusion is true. Okay, this is all chapter 1, remember it, okay? Good job. Okay, a total ordering is a partial ordering with the additional property that for all AB in the set A, if A is not equal to B, then either A is related to B or B is related to A. Now, in the examples we did, in the plane, okay, we had the case where we had 2 points that were on the circle and they weren't related to each other. Okay, because they weren't the same point. Well, they were related to each other. I'll take that back. Yeah.
You're saying you meant to say they weren't equal to each other.
Yeah, they aren't equal, but they are related. So this is B. This says or. Okay, that's an exclusive or. Okay. No, it isn't, because it's reflexive. Okay, I'll take it back. So the example we want here is something of the form, the real line is also a total ordering. Okay, so if I have 2 points on the real line, then either the first point is less than the second point, less than or equal to the second point, or the second point is less than or equal to the first point. Okay, so a total ordering is when they're total, if you pick any 2 points in the original set, they are in the relation. Okay. All right. A strict total ordering is a strict partial ordering, and if A is not equal to B, either AB is an R or BA is an R. Okay, so the strict is a strict partial ordering. Remember, it's irreflexive. So things can't be related to each other. Okay, now an equivalence relation is a relation that is reflexive, symmetric, and transitive. Okay, it has to have all 3 properties. Now, when you read section 4.5, there'll be a different definition, and then there'll be something that says that that definition is equivalent to this one. So I'm starting with this one because I like it better. Okay. Okay, now a Haas diagram, is a diagram. It's an arrow diagram without the arrows that you can apply to partial orders. And it simplifies the typical one-set diagram. It's applied only to partial orders. Now remember, a total order is also a partial order. So it's applied to total orders too. So since R is a partial order, it's reflexive, so you don't need to write the loops in this diagram if you know the relation is a partial order. So Haas diagrams don't have loops. It's anti-symmetric. So the way you write the diagram is the lower one, the arrow always goes from lower to upper, okay? So you don't have an arrow now, so the straight line is lower to upper. So when you make the diagram, you arrange your points so that where the arrows would enter, not leave, enter, are higher than where they leave. Now, sometimes you have arrows leaving and entering, but then you have another layer on top. So you have multiple layers. It's transitive, so you don't need to write all of the arrows. You only need to put the shortest link. So let's look at an example here. Oh, let's make an example. Let R be the relation on the set A, 1, 2, 3, 6, 9, 12, and 18, defined by the rule that A is related to B if A divides B. So prove A is a partial order and draw its Haas diagram. Okay. Does anyone want to try this first? At least the part about proving it's a partial order? Why don't you all try it first? And then I'm going to give you extra time because I'm going to say, this is our break, and you can try it when we come back from break. You can take your 5 right now. You can ask me any questions you want during our break.
I have a homework question.
Yes.
Okay. It is about, let me find it. I have it pulled up. Sorry. I should have been prepared. It's about number 7.
Number 7, is this on homework?
Yeah. Do you want me to read it to you, or do you want to?
Yeah, because I don't have that in front of me.
Okay. Says prove that the function g from n to n with the rule g of x equals x squared minus x is 1-to-1 but not onto.
Yep.
So I suspect there's a problem here.
From n to n?
Yes. Because I don't think it is 1-to-1 but not onto, but you're asking us to prove that. Because, for example, the input, if x is 1, the output is 0. If x is 0, the output is 0. So that would mean not 1-to-1. And as far as I can tell, it is onto n. Give me anything in n, and I can give you an input that'll get there.
That's actually a good question, and I will have to look into it and get back to you.
Natural numbers don't include 0 in
Yes,
this
they
course?
do in
Yes,
this
they do.
course. I'm sorry, Silas, they do in this class. If you look in the book, some books do not define the natural numbers as including 0. Ours does. I'm not used to that, but that's what we have to do. So I think we made this problem up. Maybe we weren't thinking of 0. But then we couldn't say natural numbers to natural numbers since 1 goes to 0. So I have to actually, let me think about this. Would you send a note in Piazza, Alex, so that we can respond? You can send it from to everybody, but in particular instructors, so we can respond to that. It's easier to respond that way, okay?
Yeah, will do.
Thank you.
Can you back to the practice problem 4, the graph one?
I'm sorry, Faze, I have trouble understanding you. Could you say it again slowly?
Yeah. Okay, maybe my microphone has somewhere. Can you back to the practice problem 4?
Well, no, people are still on break. It's not quite time yet. Thank you.
Okay, fine. Thank you.
Now it's time to resume. Okay. So who wants to give a try on showing that it's reflexive?
I can.
Great. Who's that? Who said that?
Tyler.
Oh, thank you. Okay.
So basically, to prove that it's reflexive, we want to show that AA exists in the relation.
Yep.
So if B equals A, the relation, if it exists in the relation, it'll be A divides A. And
Good.
that's a true statement, so AA exists in
Since
R.
A is equal to A times 1, then A divides A. So A is in R. Very good. And this is the way you want to say it, right? Good. All right. So now we have to show anti-symmetric. So we start out and we say, anyone want to try it? Okay, then I'll do it. We say A, B is in the relation and A is not equal to B. That's a requirement. Then B is equal to A times P, where P is in Z. Well, P is in A. And P is not equal to 1, since B does not equal A. Then A is strictly less than B, so B cannot divide A, and BA is not in the relation, so R is anti-symmetric. We good? Everybody see that? Notice how we do this proof. We start out and say, suppose we have an element of the relation. For anti-symmetric, we have to show that we have to start out saying A is not the same as B, and then show that BA is not in the relation. And that's what we did. Finally, transitive. So in this case, we have AB and BC are in the relation. By definition, then, B is equal, excuse me, to A times P, and C is equal to B times Q. Okay, where P and Q are in the integers, and that's by definition of divides. So C is equal to B times Q, which is equal to A times P times Q, where we simply substitute an equality, which is equal to A times P times Q, and that's by the associative. That's the associative law. And that's equal to A times R, R equal to PQ in Z by closure under multiplication. And this last one says A divides, so A divides C because it satisfies the definition, and AC is in R. Notice to prove this, we didn't have to go through and look at pairwise versions of this thing. Okay, at no time did we have to go through this and say, well, let me look and figure out all the elements of the relation. Okay, now to draw the Haas diagram. Oops, I thought I had this written again. So what do we have here? 1, 2, 3, 6, 9, 12, 18. K is equal to 1, 2, 3, 6, 9, 12, 18. And A is related to B if A divides B. Okay, that's our definition. So what's the lowest element of this totem pole? It's 1. Okay, now what's the next thing up? Well, 1 divides 2. And 1 divides 3, but 2 doesn't divide 3. So that's a separate branch. Now we have, the next one is 6. Well, both 2 and 3 divide 6. So let's make 6 here. We have 2 and 3 divide 6. Notice we started at the bottom and we're working up. Next element is 9. Well, 3 divides 9, but 1, 2, and 6, well, 1 we don't care about because it's at the bottom, but 2 and 6 don't. So we have 9 here. Notice 6 and 9 are not related to each other, just the way 2 and 3 are not related to each other. Then what do we have? We have 12. Who divides 12? Well, 6 divides 12, and that works because 3 divides 6, so we don't need to put anything else there. And then we have 18. Who divides 18? I think I better do this a little bit differently so I can fit it all in. Okay, so who divides 18?
9.
9 divides 18. What about 6?
Yeah, it also divides.
Notice we don't have to look further down. We don't have to look at 2 or 3 because 2 and 3 are in 6 and 9 respectively. So this would be the Haas diagram for this relation. So tell me, what would the Haas diagram for a total order look like? Remember, a Haas diagram, a total order, is one in which every 2 elements are related.
So would it just be a straight line?
And it's anti-symmetric. What would it be?
Would it just be a straight line?
Well, yeah, it would be pieces. It would look like this kind of. And so forth. So if the relation here would be, let's say, ASB, if A is less than or equal to B, then it would look like 1, 2, 3, 6, 9, 12, 18. Okay? Good. Okay. Whoop. Boy, are my numbers off. Everybody's got several different numbers. Let's try this new problem. So for S equal to the set 1, 2, 3, let's define a relation on the power set of S. So that means we're looking at the set of all pairs of subsets of S. So A and B are each a subset of S. So they're each in the power set. And the relation is defined by A is a subset of B. What properties does R have? Namely, is it reflexive, irreflexive, or neither? Is it symmetric, anti-symmetric, or neither? Is it transitive or not? So let's start out and ask the question about reflexive. for A, an element of the power set of S, which is a subset of S, is a subset of itself. Remember, we've got this subset equal here at the bottom. So the answer is yes. So A is related to A, and R is reflexive. We okay on that? If A is a subset of B, is B a subset of A? What's the only time B can be a subset of A? If they're equal. Very good. Very good. So only if they are equal. Well, isn't that the definition of antisymmetric? So if A, B is in R, then if A is not equal to B, B, A is not in R, so R is antisymmetric. Are we good? Okay, transitive. If A is a subset of B and B is a subset of C, is A subset of C? That's asking, is it transitive? This says if A, B is in R and B, C is in R, is A, C in R? Is it? If A is a subset of B and B is a subset of C, is A a subset of C? Remember what we have to do when we prove subsets. If A is a subset of B, it means if X is in A, then X is in B. And if B is a subset of C, if Y is in B, then Y is in C. So if A is a subset of B and B is a subset of C, then if X is in A, it's in B. If it's in B, it's in C. So A is a subset of C. Yes. Now you need to write down the arguments that I just said out loud. Okay? All right. Good. Okay. Let's go back and prove some stuff about an earlier section here. Let A and B and C be sets, and F from A to B is a one-to-one function, and G from B to C is a one-to-one function. Then H, which is equal to G of F, is one-to-one. How are we going to prove that? Anybody want to try it? I'll give you a chance to work on it yourself, okay? Do you remember what the definition of one-to-one is?
For every output at most, or for every output, at most one arrow goes to it.
Yeah, like a one output.
Yes, that's a very good way of
one
saying
input.
it. If it's output, there has to be exactly one. If it's called for every point in the codomain, at most one arrow goes to it. That's, I think, what you were saying, right?
Yeah, and I think it wouldn't be exactly one unless it was also surjective, right? It would just be at
Yes,
most.
very good. But here we're only proving one-to-one. So how do we start out proofs of things being one-to-one? We'll start.
For every element,
what is it? Say it again.
for every element that exists in the domain, there exists one element in the codomain that
Well,
it maps
that's
to.
true for, that's true for a function. That's the definition of function. So what we have to say, remember, so we say let x and y be in A such that h of x is equal to h of y. That's how they always start. We're trying to prove that h is one-to-one. So we start out saying, suppose we have 2 points that map onto the same point in the image of the function. Okay, then let's look and see what we know. Well, that says h equal to g of f says g of f, let me write it this way, of x is equal to g of f of y. Okay, now g is one-to-one, so f of x has to equal f of y. Okay, g is operating on those two values. So g being one-to-one says those two values have to be the same. So now what do we say? We say, oh, f is one-to-one, so x has to equal y. Hence, h is one-to-one. People write one-to-one, by the way, they say the words or they write 1, 2, 1, or if they're lazy like me, they say 1-1. They're all totally acceptable. Yes, David.
Could you do an element-wise proof? Like say, let A be an element of A is equal to 1 and only one B, and then let A, B, C be elements of A, B, C respectively.
I'm sorry, say that again.
So could you do an element-wise proof? Basically, let A, B, C be elements of A, B, and C, and then say B is equal to 1 and only.
Yeah,
like
but I
F
don't
of,
know. I don't know that A maps to B. It's not onto, so I don't know that there's anything that maps to an arbitrary element in B. All one-to-one proofs start out saying that line. Okay, and then you proceed to show, just the way we did, that that means H is one-to-one. Okay, if you start out with just picking one element of A, there's no way to show that. Now, remember, if we're trying to prove onto, then we start out and pick an element in the final codomain, which is we pick an element of C and then show there's something all the way back in A that maps onto it. Okay, so they start in different places. One starts at the beginning and proves something about the end. Well, uses the end to prove it. The other starts at the end and goes, I got something back here that solves my problem. Okay. All right. let's try another problem. Let E be a relation defined on Z2. Remember, that's Z cross Z. That's defined as X is equivalent to Y mod 3. Prove that E is reflexive, symmetric, and transitive. Do you remember? So what we know is that X is equivalent to Y mod 3 if and only if, by the division theorem, X is equal to 3P plus R1 and Y is equal to 3Q plus R2, then R1 equals R2. Okay, remember, mod means it's the remainder upon division by 3. That's what it means, modulo. So X equivalent to Y mod 3 means X is equivalent to 0 mod 3, or X is equivalent to 1 mod 3, or X is equivalent to 2 mod 3. And we can take every integer and put it in that category. Okay, so let's first say, is X in E? Well, yeah, since I'm just writing X the same time there, I have the same values for the remainders over and over again. Yes, since X equal to R1 mod 3 by definition, and R1, yeah, so we can put it on either side. Yes, David.
Wouldn't P have to be 0? Because Y mod 3 can only be 0, 1, or 2, right?
Well, I have X is, yeah. Wait, it doesn't have to be 0.
Well, because I'm wondering, because we have X equals Y mod 3. So the only possible results of any number mod 3.
5 and 8 mod 3 are the same.
Yeah, but we're not modding X by 3. We're only modding Y by 3. Or am
No, both sides are modded by 3.
Oh, okay. Just because the way I read the problem, it only puts Y mod 3 on the right side.
No,
Okay.
no. You write them the same. You only write the mod on one side. So basically what we're saying is you can make the Y equal to 0, 1, or 2, but it doesn't have to be. What it says is they both have the same remainders. Okay? Mod 3. And there are only 3 possible remainders. Okay? So if I look here, this breaks the integers up into 3 separate classes. The ones with remainder 0, the ones with remainder 1, and the ones with remainder 2. Oh, do you think that's unclear based on this writing? I'm not sure I've ever seen mod written on both sides, but if it makes you guys happier, I'll say this. X mod 3 is equal to Y mod 3. Is that happier? I've never seen it written like that, but if it works for you, it works okay for me. Grant, yes, your question.
So will there ever be an instance where it actually is asking like the way it's written? So for instance, like X would be either equal to 0, 1, or 2, like given.
Well, not the way it's written here, because this says Y is anywhere. Remember, Y is anywhere in Z. That's what that says. X, Y is in Z2. So X is anything in Z and Y is anything in Z.
Right. So what I'm asking is like, how would, if this is the same as writing X mod 3 is equal to Y mod 3, would there ever be a way to write, I guess, how it's written? Or is that never going to happen?
This is the only way I've ever seen these things, actually with an equivalent sign sometimes. That's the only way I've ever seen it written. But if you folks think it's unclear, I'll do my best to write it like that if it makes you happier. But I've never seen it that way.
In most programming languages, that's how the evaluation would proceed, is maybe where we're coming from. It's like if I read that, if I wrote that in a programming language, y mod 3 would evaluate to some constant. And then we would say x is equal to that constant.
Yeah, but I'm not assigning x the value. This is math, not a programming language.
No, I know. I'm just saying, like, if I was mechanically, like, say you told me what y was, if I was writing this down and, you know, using rewriting steps to evaluate the equation and solve for x, that's how I would proceed, which is fine. Now I know that's not how we should do it, but I'm just telling you that's my thought process, and it seems like some other people as well.
Okay. I won't say you're corrupted by programming languages, but I'll say that you're in the midst of all your programming. So we have to learn. Remember, this is a different language. That's what I tell people. So it has striking similarities to your programming languages, but programming languages don't evaluate both sides of an equal sign. It's usually an assignment, or it says, or it's in an if statement, and it's a logical one where you say equal equal in many of them, or something like that. So programming languages are much more specific, and math says things somewhat differently. So Isaac, you were asking a question. Go.
Yeah, are there any other operators that'll operate on both sides of the equivalency here? Like, is mod really the one we should be worrying about, or are there other things that are going to have a similar situation?
Offhand, I can't think of anything, but if I ever use stuff that you guys find confusing, tell me right away and we'll try and clear it up.
All right, thank you.
Christopher.
Sorry, I'm not trying to get hung up on this problem. I'm just wondering if there's a way that we could write y equals the result of the operation x mod 3. Is there a way to write that?
Well, you're talking about assignment, like a programming language.
Is there a way to write that the variable y is equal to the result of x mod 3?
Alec had a suggestion. Look in the chat. That seems pretty reasonable. Okay. So maybe, I don't know, but I want to be clear with you, and we haven't used mod very much other than the basic definition. So I don't want you to lose track of what we're trying to do, getting hung up on this definition. And we're actually out of time today. So I'm going to have to let you guys finish problem 8 at home now that you know what the definition is. Okay. Okay, somebody is confused. Grant, what you're doing is say if x is equal to y plus 3, it looks like either an assignment statement or something that just says it's equal. So this statement here is an equivalent sign. It should be 3. When you're dealing with mod, sometimes people write it equals, sometimes people write is equivalent to. Okay.
So it's just specific to mod. It's just like jargon, basically.
Yeah, what it's saying, remember in our book, it defined the definition of saying modulo is what the remainder is. Okay, so when you take x and divide it by 3, its remainder is its modulus. So when we write something like this, like that, now that we're saying it clearly, what we're saying is that after we divide by 3, the remainder of the division, using the division theorem, for x is equal to the remainder of the division by y. They're not equal, they're equivalent. So I have to take that back. So equivalent is 3 horizontal lines. And that's right,
Okay.
it is equivalent to.
So if it was the equals operator here,
Yeah, that was a mistake. Forget it.
okay.
If we're going to assign it, I'd like somebody's thing saying y is equal to x mod 3, or I shouldn't say y, I'd say r is equal to x mod 3, means there exists p such that x is equal to 3p plus r. Okay. Okay. So finish looking at this problem at home. The intent of this problem was just to look at it and see if we had something that is prove reflexive, symmetric, and transitive. Okay, let's not get hung up on this, but I'm glad you asked, and I'll try and be very clear. Please don't hesitate to ask. It helps. You notice lots of people thought something different than me. Okay? So I want to know so I can be clear so you don't get confused. How do you type the equivalent sign? Well, in PowerPoint, sad to say, what you do is you go to the symbols and you find the symbol that has the 3 lines. In Word, I guess you do the same thing. In LaTeX, there's a special sign that's \equiv. And I don't know what other language you're using. The percent sign is not, I mean, it means something else. So in the programming language, it's the same as writing that. Okay? Okay, so if you have a Windows machine, someone's got the ticket for what you can do. So I think we're going to end with that today, and we'll pick up and talk more about relations on Thursday. Remember, your homework is due Friday night. Okay, there is an exam next Thursday. We will be having review sessions on Tuesday and Wednesday. I will talk about that more on Thursday.
Thank you.
Okay, bye-bye.
Excuse me, I have some question.
Yes, Faith.
Yeah. So for simple one, if like there have a element set 1, 2, 3, 4, and the relationship is 1, 2, and 2, 3, so this relationship is transitive.
I'm sorry, I didn't understand that. Say it again.
So like if there have a set A is 1, 2, 3, 4, and the relationship is 1, 2, and 2, 3 is the relation. 2, 3, and 1, 3 is the relationship is transitive.
Yes.
So we don't all the element go to the relationship, even there the thing exists for this one is still transitive.
You have to have not all elements, but you have to say, remember, it says if AB is in the relation and BC is an element of the relation, then AC. It doesn't say that all pairs have to have something. So if you had just 1, 2, and 3, 4, then there would be nothing to apply it to. So it would be considered transitive, but there's nothing there. So this is like, if you remember in our logic, we had the logic, the truth table for if P then Q says if P is negative, if it doesn't exist, then Q is positive. If P is false, then Q is positive. And that would be the case if you didn't have A, B, and B, C. If you didn't have any of them, then it would be transitive just because of the truth table issues. Okay?
So just A, B, and B, C, which is in the relationship, and this pair C element is belong the set A, that should be fine.
Yes.
Okay, and so if the relation is reflexive and symmetric, that is another kind of the transitive because it doesn't see the A can be equal to C.
I'm sorry, say that last thing again.
If the relation is reflexive and symmetric, it's another kind of the transitive because it doesn't see the A can't be equal to C.
If it's reflexive and symmetric, it need not be transitive.
Yeah, so I was thinking because the transitive doesn't see the A can't equal C.
Well, it's not equal anyway. I'm not exactly sure what you're thinking, but we never said that they're equal.
Like 1, 2, and 2, 1. It's like A to B and B to C. This is transitive.
Yes, it would be. That would say 1 would be 1, but there are lots of other cases for transitivity.
Okay, better. Thank you.